Hello everyone, thank you for coming to this talk. So I plan to talk today about control technologies, and because this is the academic track, I'll just kind of highlight our academic success stories that we had, and if you have any interest in obtaining any of these controllers from the commercial market, I'll just point you to the company that has licensed the technology, and you can kind of work with the company to obtain those. The technology has been licensed from University of Illinois through our Office of Technology Management, but I'm here as a university professor, so I'll just present our academic work to some extent. So the vehicles you see here are UAV, Rascal UAV that flies with Piccolo autopilot. That's a subscale kind of Boeing 757 that was flown by NASA in an aviation safety program. And this is a standard kind of multi-rotor platform that you see. So what do we do with these things? We fly just better controllers. So this UAV that can be obtained off the shelf with Piccolo autopilot. So we'll do waypoint navigation and so on. So why did we have to work with it, right? That might be the question. Because Naval Postgraduate School that operates in Monterey as a Navy base had a bunch of these flying in different time-critical missions. For example, like in ISR-type missions, intelligence surveillance and reconnaissance, where they had to survey a large area to detect a potential target and so on. They had to fly a bunch of these UAVs with cameras pointing in a way to maximize the overlap of the field of view for better target detection and identification. And the onboard autopilot Piccolo, which is one of the best ones known in the market, could do waypoint navigation, but could not help them to follow very aggressive trajectories with tough curvatures and so on. So its maneuverability was highly limited. And Naval Postgraduate School people contacted me about using our controllers to improve the maneuverability of these vehicles in critical situations where they have spatial constraints, time-critical constraints, where they have to follow speed profiles with very aggressive trajectories. So they were losing the performance. So we have developed a control methodology that has proven its worth already in a number of live tests, including the NASA safety program, as I said. So, however, because this show is related kind of to agricultural applications and so on, so I'll talk in general kind of to educate people and audience about the types of vehicles we have worked with, about the methods that we have developed, and what's the advantage of the methods that we use, right? So from the perspective of kind of a general audience, so we know that the vehicles will be of two types. One will be the fixed wing, the other will be multi-rotors. Our experience is largely with flying fixed wing aircraft, so we have in-depth understanding of aerodynamics and so on. Quadrotors have been more of kind of the hobby market, berth platforms, but we have already developed also experience with those. By the end, I have just a quiz as a fun quiz to do to see how we will end up this talk. So unmanned aircraft systems, right, kind of today referred to as drones, are becoming popular, right? And here are a few just pictures just to show different types of vehicles that have crossed our path, and we had to work with those. So I will just go and introduce the characteristics and the differences for each of these aircraft, right? So fixed wing aircraft have the ability to cover wide areas, to fly fast, to survey big areas, while quadrotors and multirotors that have the ability to hover, they can basically stand and take very detailed pictures, but they will be limited in their endurance, right? So this fundamental difference has to be well explored and exploited to understand when and under what conditions which type of vehicle will be more beneficial. And today we have even hybrid platforms coming from NASA for our research, where the vehicle has vertical takeoff and landing capability due to propellers, but then its wings rotate and it transitions into forward flight and flies as UAV. So it enables you to take off and land without having a runway, but in the meantime in the air you can explore its capabilities as a UAV, so it can give you longer flight, and so on. So understanding these fundamental differences are important in terms of addressing your applications, right? So today we know that these platforms are largely needed, for example, in the context of agricultural applications. They are needed for taking imagery, for distinguishing between water damage, weed, and different types of issues that come up in farming, right? Especially in this Midwestern area where we are rich in farms. We spend about a week in one of the farms, local farms in Champaign, to understand how many different issues can come up, how chemical applications need to be applied, right? You need to spray them at low altitude, how to fly at low altitude in a very stable and robust way. These were the questions that were coming up from farmers who were kind of trying to use any of the off-the-shelf autopilots and flying low altitude with stable flight was kind of one of their challenges. So also the resolution and all the other things, all the sensors that you equip on your platforms and so on become very critical in this context. So why do we need kind of these UAVs? By the end of the day, it's the data science, right, that motivates. So we need data. We don't need UAVs, we need data. How to collect the data? We need data to do prescription farming. We need data to understand, to interpret the data. So in data science, they formulate the challenge like this, right? Data rich, information poor, data poor, information rich. It's always the battle and the trade-off in between. You can collect tons of data that may not, and you may not have the right algorithm to extract the useful information from the data you have collected. On the other hand, you may collect your data in a minimal and optimized way and have all the useful information, right? And that data collection is what asks you to fly for hours here and there, and when you fly for hours, but you don't fly the right path, you don't collect the useful data. So what am I trying to motivate here and imply? That, for example, precise path following, understanding the critical path that you need to follow, also requires high precision control algorithm. This is what motivated the Naval Postgraduate School people to contact us, because the control algorithms that we have developed are exactly enabling precise path following with very tough curvatures and with very tough spatial constraints, and under those conditions we are able to just collect the right useful data instead of collecting a bunch of data that may not be useful at all. So as I said, mission planning becomes critically important, right? And that can be achieved through advanced control algorithms. So the types of missions we have considered have included different types of spatial constraints, different types of temporal constraints. So we worked a lot with military, Department of Defense type of funding sources that were, for example, looking into problems of sequential auto landing or simultaneous landing for target suppression. And having UAVs dispersed in the air at different altitudes with different initial conditions, heterogeneous teams of vehicles. So the challenge is how to generate trajectories and speed profiles along those paths so that the vehicles could follow those with sufficient precision to enable the accurate execution of the mission. So in that process, you do image collection, image analysis, and how to represent the imagery. All these tasks are kind of motivating development of advanced guidance and control algorithms, and they have to be developed together because it's not just control, it's also the guidance, it's also the navigation. So, and this is what falls into our area of expertise, right? So here is a kind of typical multi-rotor that kind of shows what is it comprised of, but I'm sure you all know it much better than me. So then you get into the boards. So the boards you get must have sensors, kind of the right sensors you need, the GPS, IMU, and so on. Quite often we just have to keep in mind that you may need to fly in GPS-denied environments. And when you fly in GPS-denied environments, you have to be able still to figure out your own position, to have these advanced estimation algorithms based on the limited sensors that you may have. And kind of the desired properties of a good flight control algorithm can be summarized in the 4 bullets that we have here. So it should be well behaved throughout the entire flight envelope. It should be repeatable regardless of the current condition. What do we mean repeatable? Repeatable is a critical feature, and we learned it very well when working with Department of Defense applications, when they bring up all the time the verification and validation issue, certification issues, right? You want to make sure that every time you start from initial condition, you will get to the end condition along the same path, irrespective of the disturbances, irrespective of the environmental conditions, and so on. Your performance has to be repeatable. It shouldn't change. It's not enough just to be stable every time. You want also to have the same transient performance, right? If these words are communicating something better. So it's not just enough to be stable every time to come to the origin. You want every time also to have the same transient performance. This repeatable performance is critically important for certification, verification, and validation purposes. And when you don't get this performance, then your safety is not guaranteed. You are compromising actually safety, okay? And that predictable performance, as I'm saying the next, predictable performance is also critical, right? So you want to know if I'm flying in these conditions, you want to make sure that you can predict your performance. And if you have done some analysis offline and you have developed a control algorithm and you have certain guarantees for your control algorithm and it flies, what if the conditions change? What if some unexpected obstacle happens or something unexpected wind, disturbance, gust, and so on happens, right? You want to be able still to predict the performance of your control algorithm irrespective of the conditions. You want to be sure that it will have graceful degradation of the performance. It won't give you anything unpredictable, but its performance degradation will be graceful. There is a nice example that I always give to parallel this. So when I first moved to Illinois, I had no experience of driving my car on ice. And the first week we had ice in Illinois, I got a car accident. Why? Because the car was not giving me the predictable response. I was braking, it was sliding, and I was trying to brake it even harder, and it was sliding even worse, getting me into an accident. Then people explained me that in these conditions I should not brake, I should instead just do the opposite, drive slowly. In 2 days, I repeated my accident. Why? Because I was not used kind of to operate the vehicle in unpredictable circumstances when it was giving me unpredictable response, right? So you want always to get a predictable response. For safety, it's critical. Imagine if something like that happens with a pilot and he gets unpredictable response and he tries to do corrective action, he gets into so-called pilot-induced oscillations, which is the main cause of aviation crash. Right? Of course, we are talking here about UAVs and quadrotors. The pilot is not on them, but aviation safety gets judged by these metrics, right? You want safe, predictable flight, and you want every performance to be repeatable so that you do not have to do corrective actions and so on. So moving forward, I will introduce the L1 adaptive control that we developed that has all these features that I was discussing here. For example, here is a kind of a flight which was recorded in Germany. So you see here one motor is taken off, and without one motor, this thing will still fly very stable. So I will show a few more movies. For example, this one, we'll see how it flies. It does free falls without going into hover, without going into the stabilizing effects, without going into ground effects. You will see it's free falls now as it starts taking off.
Can you talk a little bit more about Jimmy's about the requirements for doing this and airframe armament versus PFDs?
Well, PID is okay. I will surely say. So when it goes now up and it starts doing the free falls, I just want to show the stable flight as you watch. So it will do free falls without destabilizing. I'll reduce the noise so I can comment more. So PIDs are non-model based control approach. Okay, so I will now distinguish between. Look how it does free falls without going into destabilizing effect. So it basically does not start wobbling as it does free falls, so it handles the aerodynamics pretty well. So, and this is now kind of position hold of it that it would do. And so let me talk a little bit about the PID versus the L1 adaptive control, what was the title of this slide. PID is a non-model based control approach. So it has three gains: proportional, integral, derivative. If you code it, right, you attach it to anything, be it your quadrotor, be it your dishwasher or refrigerator or something else, or a ground robot. It has three gains. You will start playing and tuning with it. If you know your own system very well, you have lived with that system, you have grown with it, you will quickly figure out how to tune these PID gains to make it fly. But when your conditions change, that PID will need retuning, right? You go from one airframe to another, you have to go and retune your PID. Something changes, you have to go and retune the PID. Because that PID is not model-based. It's just a control block. It's an ideal dream to have something you would attach to anything, and it will control it very well. L1 adaptive control, on the other hand, belongs to so-called, it's almost over. L1 adaptive control that stands there belongs to the class of model-based controllers. So what's the difference between non-model-based control and model-based control? Okay? Model-based controllers take advantage of your knowledge of the model. If you have gone to school and this is academic track, you had most likely some control courses or even dynamics courses. You have learned Newton's laws, you have learned Euler-Lagrange equations. Well, let's say Newton's second law, everybody should know from high school physics, right? So you use some basic principles of physics to model your system dynamics, right? The real models are very far from the textbook models that you would get, like with F equals ma, right? Newton's second law, you will get some model because it says the second derivative of your position equals the forces divided by mass, right? So if you use it and you come up with some state space modeling of your system, some variables, you will have some equations to work with, right? You can improve always that model to make it as close to the real one as possible. For example, the aerodynamic forces are hard to model, right? Disturbance, gust, these things are extremely challenging to model. So you can therefore enhance your model starting from basic principles. You can enhance your model with any additional data that you get. But for that, you need to know system identification, a little bit more mathematical, rigorous approaches that would help you to improve and enhance your models, to work with those, right? Once you have a model, you can develop a model-based controller that can be any of the robust controllers known in the world. If you have heard H infinity, if you have heard linear quadratic regulator, LQR, LQG, L1 adaptive control is also a model-based control, right? The beauty of L1 adaptive control as compared to these other approaches that I just mentioned is that it has a very easy structure for its realization, and it easily scales from small system to big systems, and it has a lot of other nice properties that we have explored, and I'm happy to talk about all of that in private meetings if you are interested. Now I just want to go ahead with the presentation. So here is, for example, one of the beauties of L1 adaptive control. The Rascal model that I showed, for example, with the Piccolo autopilot, when tuned perfectly to follow the path, like you see here, when you see here the red path that it was tuned to follow, upon a payload change, it goes into oscillations, right? So this is why the Naval Postgraduate School people approached us asking if L1 adaptive control could be used on the top of the Piccolo, because Piccolo comes as a black box and nobody can edit the code. They said, can we have an L1 augmentation loop around the Piccolo to improve its performance so that the path following could be enhanced, right? And this is what we helped them to achieve. These are real flight test data, right? So. And here is something that we flew at NASA that we are very proud of it. So here is the subscale commercial jet, which is flying with the pilots. If something is trusted by the pilots, it means it has maybe some credibility. So it's a twin jet engine, so they power it. How it flies with the so you see this antenna on the top of the truck. The pilot is inside the truck, and he's flying it as if he would fly the real one, right? And then this small bomb flies. So what was the motivation for behind this development? The motivation was that for the past 50 years, control theory has been significantly advanced, but despite that, all the commercial airlines until now are flying with the control techniques from 50s and 60s. The transition from the academic research to the real commercial airplane goes through wind tunnel testing, for example. And wind tunnel testing does not provide enough credibility to put it on the real airplane. Therefore, NASA came up with this concept of flying wind tunnel, where they said, we will build a truck where the pilot will sit and he will be given the environment of the feeling that he's flying the real airplane. In the meantime, the subscale one will be flying. So this antenna on the top of the truck is communicating the control signals to this 5.5% generic transport model aircraft, which is kind of being tested for various failures, delays, discrepancies, and so on. So in these conditions, I mean, this was a 2-year program funded by NASA. And among all the controllers that were funded by NASA, this was the only controllers that the pilots cleared for stall and post-stall flight. I don't know if you know what is a stall or post-stall flight. Every aircraft, imagine even the fixed-wing UAV, when it goes to a critical angle of attack, it starts losing lift. When it starts losing lift, it goes into roll oscillations. When it goes into roll oscillations, it falls. So what L1 adaptive control managed to demonstrate, that when you go into stall, you won't go into roll oscillation. You will still lose your lift. But because you don't go into roll oscillation, for pilot it becomes much simpler to put its head down and to pick up again. When it goes into roll oscillation, it's extremely hard for the pilot to put the head down and pick up the aircraft again. So it gives a completely controllable aircraft to the pilot under extremely critical, severe conditions. And this was the only controller that the pilots cleared for post-stall flight. They intensively used it for modeling the departure edge of the flight envelope. When I was talking of modeling and the critical need for having good models for developing good, reliable flight control systems, you say safety, you say reliability. You can't go with PID. That was the modeling group that you just saw on the screen, who are downloading the data to update the aerodynamic models. To fly a toy in this room, you can fly anything. You can get it from 3D robotics, from different companies, and get the toy flying here. But when you want to talk about having serious platform out there operating, you want its performance to be guaranteed. You want its safety never to be compromised, right? This is not a toy experiment in your university lab. We are talking about flying outdoors, flying in severe climate conditions, rain and shine. I don't know, different kinds of environmental disturbances can hit you and hurt you. So therefore, this program had the objective of advancing. Here is, for example, how it pulls into post-stall flight, and how they use it to update the aerodynamic models at the departure edge of the flight envelope. And this controller just proved its worth under these conditions. So here is how they will pull into stall. If you look, the stall occurs at 12-13 degree angle of attack. This is the stall condition. I see that some of you are very well familiar with these flying qualities. Maybe some of you have pilot's license, have flown. So the aircraft goes into stall and the controller handles it, right? So having the controller handling this much is what makes it attractive for different commercial applications, and we have therefore kind of licensed the technology to a company through University of Illinois. So this is what an experiment that students did at Technical University of Munich. So look, this is Ascenta Technologies platform, one of the well-known German companies. It's called Hummingbird, I think, this platform. They attach a tape. It's pretty stable, but it loses a little, it drifts a bit at the additional weight. This is student project. They wrote a nice paper on it. It goes back when they cut the tape. It comes perfectly tuned with its PID, or I think dynamic inversion, whatever it has. Now they switch to L1, and this is what happens. Look how it handles it. Right? So this is what makes it attractive for agricultural applications. If you want to spray from a uniform altitude, if you want to have fertilization done very uniformly, you won't have any drift from the change of the mass, right? And having said all of this, here is also the Eurocopter model that kind of also they funded it to have the controller running on it. So this is just a simulator. It's still not in production, but here it is. So it's available also from some of the links on our YouTube channel. So as I said, so guidance navigation, it's not just the inner loop robust autopilot that you need, but you also need advanced guidance navigation control algorithm. What you see here is a waypoint navigation, right? But what if you have very aggressive curvature and you want to have precise path following? Because it's critical for your crops, it's critical for the kind of yield to maximize it, and therefore, as I said, we need very accurate path following algorithms and so on. Here it's, again, the picture is taken at Camp Roberts, California. That's where the Naval Postgraduate School has access for unlimited flights. No FAA regulations could stop them. And here is where we were able to mature the control algorithm for commercialization. So this is like a coordinated path of vehicles and collision avoidance. See this object when it's coming, there is speed adjustment. So it would have collided if there was no speed adjustment. But because there was speed adjustment, it picked up to avoid the collision. So we are coordinating multiple vehicles, and this illustration is just showing. So the light gray one was the original path. The dark gray is what the adjusted one was to avoid the potential collisions with potential obstacles. And these algorithms we are developing jointly with NASA. The students did summer internship there in summer, and this is like showing loop collision. This is coordinated path. They arrive simultaneously at the end, and this is like chasing. Look, one flies a bigger radius, one smaller, but they are coordinated, so they always remain on the same line. This is like different coordination objectives. These, the two multirotors, okay, that's a good question. So the two multirotors are talking to each other, sharing specific information. And the challenge is here what to share. Here is where math becomes critical. If you measure your position with your noisy sensor and share it over a network that has its own additional noise, right? Then most likely you are not sharing a nice, good information for the other multirotor to take his decisions, right? So therefore, what we share over the information, over the network is something very mathematical and clean. I never share my state measured by my noisy sensor, but I compute so-called virtual rabbit along the path that I would like to follow, and along the path that I'm trying to follow, I assign a virtual rabbit with its speed profile, which I'm controlling. And because I'm following the rabbit and I'm controlling also the speed of the rabbit is a virtual variable in my computer. It's clean, and I'm exchanging that. So they are exchanging the coordinates of the virtual rabbit that they are following instead of exchanging their states. And with that, they are minimizing at least the noise of their own sensor is not being transmitted over the network. So the quality operative part of the algorithm deals only with the nuisances of the wireless communication, and you are clean from your own noisy sensors and so on. This is where the science is, this is where the students get PhDs, so we are figuring out all these algorithms, coming up with performance guarantees, with the underlying assumptions that are critical to make all these claims hold, and so on. So this is where we kind of win, right? So when talking, for example, to some farmers, which we have done, and asking them what is holding you back from investing in a UAV, the typical answer is landing, flying, and taking off. So, I mean, when they are up in the air, right, it's much easier to fly than to take off and land, right? And for a farmer to learn in general how to do this entire process, it's extremely challenging. So what do they want? They want safety first, survivability must be guaranteed at all time, all features must be easily accessible to the user, you want a very nice user interface, right? Today if we talk to a high school kid or even a middle school kid who doesn't know any programming, who hasn't ever explored the computers, maybe besides Facebook or social sites, right? They will be able to use the iPhone very easily and operate the iPhone. Why? Because it has very easy user interface, right? Interfaces are critical to translate the very advanced science into something very usable, very practical, right? And this is what we emphasize already through the development of the company products. As I said, the technology has been licensed to the company, but that can be a separate talk, so I don't want to go into that part. So if you're interested, I can put you in touch. So users should require no knowledge of system internals, and this is critical for getting good products out there and in the hands. So here is what when I was talking of coordinated flight, and you said, why should we coordinate? Here is two UAVs, completely heterogeneous, with different cameras, different degrees of freedom, different gimbals, and they have to scan the road, and on this white road, there is a moving target that they have to find and then identify. So one of them flies low altitude with 2 degrees of freedom gimbal that can scan the area but has poor resolution. It's not capable of tracking it. The other UAV that flies higher altitude has 1 degree of freedom gimbal, very fixed, narrow, but very high resolution. By sharing information over a network, both of them are able to follow the same road, and by pointing the cameras in a way, they are maximizing the overlap of the field of view to find the potential targets on this road. So 5 minutes of training, right? So the alternative, is the Predator station that we know that takes forever to make it work. So with acknowledgement, so I would like to kind of acknowledge the companies that we have worked with, the Department of Defense agencies that have funded our work at University of Illinois. This Raymarine autopilot was the first autopilot commercialized by Raymarine for boats. It's downloadable. You can download and obtain it from Raymarine website. If you have nice boats and you want to go out into the ocean, it uses L1 adaptive control. Intellinear is the company that commercializes the drones. What you see here is the Learjet that's flying now. If you tune into our YouTube channel or into our Twitter site, from my university website, there is a Twitter link. You will get daily updates of the Learjet flight tests that are flying with F-16 and B-52 pilots, testing the controller for various aggressive conditions. There are 2 hours of flights every day, 2 deployments. Every deployment is 2 hours of flight. And the daily updates are coming from every flight, how the flights are going. It's very intense. I am flying to Edwards Air Force Base myself this Sunday. And now I want to do the small quiz. I just want to get some answers to understand how to drive my research further in this area to be more helpful for farming, for agricultural purposes, and so on. So how many of you want to have your own drone? Can you raise hands? So that's 12, 11. How many of you would rather have a service company instead of having your own drone to come and get the data for you? 2, 3, 5, okay. So how many of you already have your own drones and have got FAA warning letters? Nobody would say.
No one's going to raise their hand for that.
But okay, how many of you have the drone and have not got the FAA letter? Okay. Okay. So the first question is the winner, right? So by how much you predict that you can improve your yield if you were able to take frequent data information to guide your fertilization with control or pest control strategies? What do you think? How much you can improve it if you got the right data at the right time?
More than 30%.
More than 30%. Okay, good. Thank you for the quiz. And I think I am on time, right? So.
You're perfect. If anyone else has any questions.
Right, so here is the information. So you go to our webpage, our YouTube channel, and the company that you can kind of contact for getting the autopilots or drones if you want. So. And with that, oh, there are already backup slides, so I'm happy to take questions if you want. So backup slides are here. So can I turn off already? Right.
From a production agriculture standpoint, that last 10 to 20, 30% increase in yields, what, with this data you're trying to get, what are you doing to move forward to?
I want you to tell me so that I do my research. So that's what I would like to know, because I'm in academia, right? I'm doing research. My production is measured by the number of papers we write. But because I closely work with so many companies, I showed, right? Boeing, Raytheon, even Seagate is interested in the controller, and there are this, Raymarine is commercializing, and Intellinear is commercializing. So I work with companies, therefore I'm very much interested in practical questions. And if you answer that question for me, I am happy to go and get my students, and then we do some research. And we work also with agro professors from University of Illinois, so we have a lot of exchange of information with different campuses and colleges. More questions? No more questions? Interesting? So thanks.
Awesome. Well, thank you for a great presentation. We appreciate it.